So in a previous set of videos, we looked at the concept of the DC to AC converter, and we called it an inverter. If we wanted to go the other way, from AC to DC, we call that a rectifier. And topologically, a lot of these circuits are very similar. The rectifiers and inverters, they can be used interchangeably in a lot of cases, although practically they might not be, but functionally they can. So what we're going to do in this set of videos is we're going to look at the rectifiers. Now, there are many types of rectifiers, and they can be single phase, they can be three phase, they can be half wave or full wave, but they all operate on the same principle, and that's you're converting AC into DC. Okay, and the DC that we're talking about here is DC in a sort of electrical engineering sense, not a purely mathematical sense. And what I mean by that is the DC, or the output component, or the output voltage, current, whatever you're looking at, has some ripple. So it's not a pure DC, but we can filter it to a point where it will become some type of DC. When we say DC in this case, we're really referring to a unipolar current. So the current will be positive or negative, I guess, depending on the way it's drawn, but it will be in one direction only. Okay, so I should also add that the diodes that we're going to be looking at are going to be assumed to be ideal in this case. So they will have zero voltage drop when they turn on, and they will turn on for any voltage greater than zero. Okay, so the simplest case of the rectifier is the half-wave rectifier, and you may have seen the half-wave rectifier in an introductory electronic course where you study semiconductor devices like transistors and diodes. But we're going to start with this because this is a good place to start because it's familiar and it's the simplest case that we can have, and it illustrates the concept very clearly. So we have a sinusoidal source, Vs sine omega t. That means the source is operating with a frequency of, or angular frequency of omega. We have this diode here. We're going to say that this current here is ID. We're going to call this resistor here R, and we're going to assume that the voltage drop across the resistor is Vd. Okay? And so I'm going to cheat a little bit because there's lots of waveforms in these types of circuits, and since these are drawn very clearly and they illustrate the concepts quite clearly, it's better to use those than to struggle with these myself. So what's happening here? So we know that Vs, or this voltage source, is a sinusoidal source, and we know obviously that sinusoidal sources are positive and negative. So in reality what's happening is this sinusoidal source goes up, it comes down, and then it goes below zero as well. Something like this, obviously not drawn to scale, but for the purpose of demonstration, I guess, it'll do something like this, right? It'll go below zero, but what happens here is when this voltage goes greater than zero, the voltage across the diode, I guess we can call this the voltage across the diode, let's call it VAK, so anode to cathode. So VAK becomes greater than zero when VD, or I should say Vs, is greater than zero, right? So when that's greater than zero, the diode turns on, it begins to conduct, and you'll see that because the load is resistive, the current profile is the exact same as the voltage profile. So the shapes of the waveforms are the exact same. And we expect that obviously because it's a resistive load. There's no distortion, there's no delays in current, there's no leading or lagging or anything like that. So that's fairly straightforward, and we see that also that the amplitude of the current here, the amplitude of this current is equal to Vs, so the peak of the voltage divided by R, which is also expected. And so we also see, I guess the most obvious characteristic is that when the voltage drops below zero, the output, or the source voltage, I should say, drops below zero, we see that this voltage Vd remains zero. This is why we call it a half-wave rectifier, because it only rectifies half of the wave and not the full wave. So whenever it's below zero, you don't get an output. Now this is obviously less than ideal, and by less than ideal I mean like it's not a good thing, because you're losing half of the cycle, and there's no real benefit to this other than you have a very simple circuit. But still, this is the simplest type of rectifier circuit. But the problem, again, like I mentioned, is, well, one is that you're not using the whole period, and the other is that the output voltage and current in this case have a ripple at the AC input frequency, right? So the frequency of this ripple at the output is also the same as the frequency of the input. Okay, that's not a good thing because that's difficult to design for to design filtering around, and so this is difficult to filter. So typically we don't use this circuit, but it's a good place to start. So I should get that out of the way as well. Like, this is not a practical circuit these days. It was historically speaking, because back in the day they used to use vacuum tubes for this type of stuff, and vacuum tubes had really large voltage drops, so you wanted to minimize the number of vacuum tubes you used. And so in that case, having only one diode or vacuum tube acting as I guess essentially as a diode as well, having only one of them was beneficial. But nowadays we have much more elaborate rectifier topologies because we can afford to, because now with the popularity of silicon, you have much lower voltage drops across these devices. So in this case, VD and ID will have the same polarity at all times. And if you want to confirm this, you can use what we call the method of assumed states, which is something you would learn in electronics. Essentially what we say is you assume a state for the diode and then you check the circuit conditions to make sure that the circuit behaves in agreement with all of the conditions that you assumed. So if you want to assume that the diode's off, then the diode current has to be 0. So you can prove all that kind of stuff. We won't go through all that kind of stuff here because it's a very simple circuit and you see what's happening in front of you. For more complicated circuits, we might have that kind of discussion. But still, what we're concerned with is the DC component, right? So the DC component of this output, will be something like this, right? I mean, again, this is roughly drawn. It's not certain that it's like this. There's no reason I'm drawing it like this, except that the average has to be something less than the peak, obviously, because this is off for half the cycle. I'm assuming it's somewhere in the middle. In reality, it'll probably be even lower than that if I want to draw it accurately, but I don't really care to right now. So this is going to be VD average, okay? And so how do we find the average of VD? What we do is we integrate the function over the period, and then we divide it by the period. So if we do that, we say VD is 1 over 2 pi, which is the period, and we integrate from 0 to 2 pi, and this is Vs sine omega t, and we're integrating d omega t. So the phase is going from 0 to 2 pi. And if you do this integral, which is a very simple integral to solve, you'll see that this is Vs over pi. Okay, so the output average is Vs over pi. And that's true for all half-wave rectifiers. That would look like this, regardless of whatever you have. So you see that it really just depends on Vs, your output DC component. So the function of the rectifier is to produce an output with a low ripple content, right? You want to obviously have low ripples because the larger the ripples you have. So if this goes between Vs and 0, this is obviously going to introduce some type of noise into your system, which is obviously never a good thing. And so what you want to do is you can use low-pass filtering between the rectifier output and the load. So the output of the rectifier, I guess if we were to think about it here, we can say that this is the output of the rectifier and then the resistor is the load, right? So you can use a low-pass filter, and that could be any low-pass filter that you want. It could be a series inductance, it could be a capacitor. The two have their own benefits, obviously, but filters can change the operating characteristics of the circuit. So in that case, the average output voltage could also change. So let's take a look at a slightly augmented version of what we're looking at here. And what we're going to do with that is we're going to take a look at the half-wave rectifier, but with an inductive load. Okay, so if we have an inductive load in the exact same circuit, and I guess you can also consider this to be some type of filter as well, because I mean it's not part of the rectifier, right? So it must be, I guess, part of the load, and its effects will be seen on the load side. So what do we have here? We have here, we're going to call this L, we're going to call this R. Of course, this is still VD. This is still Vs sine omega t. That's still D. We have to draw our diode current here, ID. Okay? Sorry, I made a mistake. This is not VD. VD is going to be the output of the rectifier always. So this is VD. Okay? Cool. So now what I'm going to do is I'm going to cheat again, and I'm going to pull in a waveform. And so this is the waveform we have here. So we see something that's slightly different here. And remember last time I said because this is a resistive load, we expect the current and the voltage to have the same shape. In any load that's not resistive, that won't be true anymore. So here we've introduced an inductor L, and what this will do is this would filter out certain harmonics, mainly would filter out the current. And so you would end up having a slightly different shape in the current. But it would also introduce a phase shift between the voltage and the current, as inductors do, because now if you want to think about it in terms of power factor, now the power factor is no longer 1, right? Or if you want to just think about it, you've added a reactive component here. So the overall thing shifts according to whatever the combination of these two is in the complex domain, right? So what are the two main differences here? There are two key differences, and if they aren't obvious to you, we can discuss them. So one is that this voltage goes negative, and this voltage here goes negative. So you'll notice VD is no longer constrained to be positive. Now why does that happen? Because what's happening in a case like this is when this diode turns off, well, the simplest thing is that you can't force an inductor's current to go to 0 instantaneously, right? And as a result of that, it will still have some voltage across it so long as current is flowing through it. Now, in this case, the current is changing, therefore there will be a voltage. If the current was constant through the inductor, then there's no change in inductor current, therefore no inductor voltage is developed. Here, this is a changing voltage, and therefore you'll have a sort of changing current here as well, right? But the more important thing to think about here is that there is a shift now between these two, right? So the two don't rise and fall at the exact same time. Therefore, you can't say that VD will go to 0 at the same time as this ID, because this inductor forces it. Well, I guess not. Well, yeah, I guess you can say forces it or keeps it up, right? So it stays up. Therefore, VD is allowed to go negative. And then as soon as it goes to a certain point where the inductor current reaches 0, at this omega t1, inductor current goes to 0, and all of a sudden this diode is forced to turn off, so you see this voltage snaps up to 0, right? So there's ways to, I guess, reason through all of this and to make sure that all this makes sense. I mean, if we think about it, the circuit must operate in a cycle, right? So the diode has to turn off for some period of the cycle. We have to have that. If it doesn't, then what would happen is that VD, if this diode's always on, then VD ends up being equal to Vs sine omega t, meaning that this average has to be 0, because the average of a sine wave is 0, right? But VD's average being 0 means there will be no current flowing here, right? So if VD's average is 0, that means this resistor's voltage average is 0, meaning the current that would flow through here would also be 0, right? And having a finite value of L means that there must be a non-zero current. And we know that this diode would not allow reverse conduction. So we're seeing all these inconsistencies here is my point, right? So the diode can't always be on, and ID must be 0 for some part of the cycle. So this will happen when Vs is less than 0, and the diode will turn on when Vs crosses 0 from negative to positive. Okay, so that's what I mean when I say these inconsistencies of the method of assumed state. So that's what I did. So I assumed that this was always on, and I saw a bunch of inconsistencies. If this is always on, then this average voltage is 0. That means this average voltage is 0. That means this current is 0, but this current can't be 0 because this inductor exists. So you see that there's a whole bunch of things, like everything kind of just dominoes, and you see that the whole thing falls apart. And that's the kind of inconsistency you're looking for when you do this method of assumed states. But in a case like this, we know that VD will depend on R, and the placement of L, I should also add, is not unique here. So since most sources will have some inductance, and what I mean by it's not unique, I mean like you can put it here or you can put it here. When the two components are in series, it makes no difference, right? So the overall impact on the circuit is still the same. VD's behavior may or may not change, probably will, depending on what you're trying to do with it and what you're trying to measure. But the fact that L is placed after the diode or before the diode changes nothing. And in reality, we know that a voltage source is not ideal, and usually there usually is some type of series inductor with the voltage source, which has to do with the internal magnetics. If it's coming from a source that's like a power system, that might have to do with like the actual inductance of the system, but there's always some equivalent inductance in series with these voltage sources. So this is a more practical circuit, than the purely resistive circuit that we saw in the previous case. But one of the things that we're seeing here is that there's this zero period, right? So maybe I should use a different color here, something that's actually readable. So we see that ID goes up and then it goes to zero during this time. So it stops conducting. So there's a sort of discontinuous conduction here, right? And so we're going to leave it here for now, but we see that this could be a problem in some cases, right? And so what we're going to do in another video is we're going to take a look at how we might be able to make sure that this this current never goes to zero, and how if it stays above zero, because then you can have a continuous conduction, which may be favorable in certain circumstances. So what we did here is we introduced the concept of this half-wave rectifier. We sort of reasoned with how it should operate overall. We determined its average voltage. The average output voltage is Vs over pi. And what we're going to do is then, to eliminate harmonics and to have a more accurate model, we said that we might have this inductor L. Okay, and if we have this inductor L here, then we see that the current and the voltage are no longer in phase, and that they're actually displaced, and that in this case Vd actually goes negative. Okay, and we saw that in this case the current still goes to zero, but that might not be favorable, and we're going to introduce a way to eliminate that in a future video. So if you have any questions, leave them in the comments below. I hope this was helpful. Like and subscribe to support the channel, and we'll see you in the next one.